let's try to solve this problem here. The temperature in outer space is about 3.5 Kelvin, and it is estimated that there is about 1 hydrogen molecule per cm cube. Okay, so to extract the information here, we know that the temperature is 3.5 Kelvin. We don't need to convert it to other unit because that's what we are going to operate with in Kelvin. And after that, they say that there's about 1 hydrogen molecule per cm cube. Means by the outer space is very wide, okay, definitely more than 1 cm cube. But if you look into 1 cm cube of volume in outer space, if you focus on only 1 cm cube, okay, 1. If you look at just 1 cm cube of the outer space, you'll find on average there will be 1 hydrogen molecule inside that 1 cm cube space here. Okay, you'll find 1 hydrogen molecule here. Okay, then they say that the mass of the hydrogen molecule is 3.346 times 10 to the power negative 27 kg. So this one is mass of one single molecule. Mass of one single molecule is m is equals to 3.346 times 10 to the power of negative 27. Okay, so you are given the temperature, you are given the mass of hydrogen molecule, but some of you might have trouble to interpret this information here, which is 1 hydrogen molecule per cm cube. What does it actually mean? Okay, if you think about it, 1 hydrogen molecule, it's telling, if you put it into fraction, what it means here is 1 molecule for every 1 cm cube. For every 1 cm cube, we are going to find 1 molecule, 1 hydrogen molecule inside it. If it's 2 cm cube, then you'll find 2 molecules inside it. If it's 3 cm cube, you'll find 3 molecules inside it. It's a ratio kind of thing. Okay, so you can see that 1 molecule represents the number of molecules inside the 1 cm cube. Then this is the volume of the of what we are interested in. So actually what you are seeing here is actually the number of molecules per unit volume, N over V. Okay, so these are the information given to you. Now they ask you for the RMS speed and the pressure. Okay, again we bring out our summary from the explanation video. We have pressure being related to your translational kinetic energy. Which is KTR. Then you have your temperature, which is T. Then lastly, you have your root mean square speed. Root mean square speed. Okay, I believe you are aware that we already derived everything actually in the explanation video, that in this situation here, they are giving us a temperature. The temperature is indicated in this side of the rectangle, and they ask you to relate it to RMS speed. So you are going to relate it to RMS speed. That means by you are going to pick equation that is in this, on this side of the mind map over here. So on this side of the mind map, we have 2 equations available. One is V RMS is equals to square root of 3 RT over the molar mass. Another one will be V RMS is equals to 3 KT over mass of one single molecule. So there's 2 equations for us to pick, equation 1, equation 2, and I believe in this situation, equation 2 will be more appropriate. Why are we going to pick equation 2 is because they give us the mass of one single molecule instead of the molar mass. They're not giving us the mass of 1 mole of hydrogen gas, they're giving us the mass of one single hydrogen molecule. So in that case, using a per molecule kind of equation will be more appropriate here. So we pick our equation already. So for question A, we are going to use VRMS, the root mean square speed is equals to the square root of 3 Boltzmann constant, the temperature, divided by the mass of one hydrogen molecule. Okay, so the rest is just substitution. 3, K is 1.38 times 10 to the power negative 23. Then you have your temperature, which is in Kelvin, 3.5 must be in Kelvin. If you get degree in Celsius, make sure you convert to Kelvin. Okay, then your mass of one single molecule will be 3.346 times 10 to the power of negative 27. Okay, so from here, if you do your calculation, I believe you are able to get your root mean square speed to be 208.6 0.10 meter per second. Okay, done. So that's question number A. Question B, you get pressure of the hydrogen gas at the outer space. So now you get your root mean square speed. They want you to further do your calculation in order to obtain pressure. So now you are on this side of the rectangle. You are on this side of the rectangle. And on this side of the rectangle, you have again two equations also. First, you have PV is equals to 1 over 3 Nm VRMS square. Then you also have P is equals to 1 over 3 rho VRMS square. So there's two equations available to be picked. And I believe for this situation, you can see that there's not much information that can indicate what's the density of it, or you can say the density is difficult to be obtained. So in this case, using the first equation will be more appropriate, but we need to do a bit of manipulation over here in order to make the equation usable. Okay, the equation that we get is PV is equals to 1 over 3 Nm VRMS square. And I believe you see that the information given here is N over V. It is not, they don't give you the number of molecules in outer space. They don't give you the volume of the outer space. That would be a bit too difficult to determine actually. Okay, so they give you the number of molecules per unit volume. So what can we do to this equation here? We can manipulate by shifting the volume to the right hand side, making the V to be underneath. Okay, so we bring the V from the left hand side to the right hand side. So now it becomes a denominator. Then the rest remains the same. Okay, so we can proceed with our substitution, but before we substitute, we have to be aware that for our N over EV here, the unit is in per cm cube. Per cm cube is not SI unit, so it's best that we convert it to meter cube, per meter cube first, before we do our substitution. Okay, so this is 1 molecule divided by 1 cm cube. We wish to eliminate this cm cube, we do 1 cm cube, instead we want it to be in SI unit in meter cube. So later when you do your calculation, you are able to cross out the cm cube because they are on both sides of the fraction, on the opposite side of the fraction, then you are left with per meter cube as your answer. Okay, we are aware that 1 meter cube is equivalent to 100 cm, but in this case there's a cube over here, so we're going to cube the value over here. So if you cube the value over here, what you get is you get 10 times 10 to the power of 6 per meter cube. Okay, why is it m negative 3? It's because you cross out the cm cube over here, then what's left is meter cube, but meter cube is at the denominator, so it's m negative 3. So this is the number of molecules per unit volume. Okay, so you obtain the correct unit already, so now you are just left with substitution. Okay, so let's do our substitution. You are finding pressure, so leave pressure as it is. The number of molecules per unit volume is times 10 to the power of 6. The mass of one single molecule is 3.346 times 10 to the power negative 27. And our VRMS square, VRMS you obtained from previous, okay, I'm going to write down here. Previous question tells us that it's 208.10, so square. From here, you're able to get the pressure to be 4.83 times 10 to the power of negative 17 Pascal. And actually, if you look at this value here, this value is very, very low in terms of pressure. Okay, so that's why we can say that outer space is actually near vacuum. We consider it to be near vacuum because there's little to nearly none, little amount of gas molecules that you have in the in outer space. Therefore, because you have very little gas molecules in the outer space, the collision that happens is very rare compared to our atmosphere. Let's say there's a rare amount of collisions. So because there's rare amount of collisions, the pressure will be very, very low. Okay, so you can see here the pressure in outer space is in the negative 17 kind of range. Compared to our atmosphere is around times 10 to the power of 5 kind of range. Okay, so there's a stark difference over here, and I hope from this question you are able to understand why. It's because of the very little amount of gas molecules that you have per unit volume in the outer space.